Yeah, so I hope you're good, guys. For on today's session, we're gonna be looking at the subspaces since we've covered this topic before. So I want us to just go through it again. Then we look at this time. We're gonna be looking at the proofs instead of looking at the examples. So on this one, we're just gonna look at one proof, which we need to prove that a subspace or a subset of a vector space is itself a vector space. So if it's like that, we can now call it a subspace. So when you come to the subspaces, I can first say that we need to know how to define a subspace. So remember I said that if we have W being a subset of V, given that V is a vector space, given that V is a vector space, and we know that in this case W would be non-empty, right? W would be non-empty because obviously V is also non-empty, should contain at least the zero vector. And another thing that will happen is that this one, remember I said that for this to be a subspace, it should itself be itself is a vector space. So it's going to satisfy the following properties. Zero vector should be found in W. We should have that if I take a vector V plus a vector U and I add them, I'll find them in W. And also if I take a scalar K from a field F and then I take a vector from W, I'll find that it are found in W if I multiply them. So this is the scalar multiplication, vector addition, and the zero vector. So given this information, we can be able to define what is a subspace, right? We can say that we are talking about, we can say that this is a non-empty subset. And this subset is of what? Of a vector space. And what is our vector space in this case? Which is a V, right? So we are saying that a non-empty subset, let me just say W, a non-empty subset W of a vector space V is called, so we can say that is called a subspace. So this will be called a subspace if it is itself a vector space. You see what I mean? Subspace if it is itself a vector space. You see, right? And it should be a vector space under what? So we can say under, and I can say under addition and scalar multiplication. So the zero vector has been covered here on non-empty subset. You see, right? When I say that it is non-empty, in other words, I'm saying that at least it should have inherited the zero vector from the vector space V. You see, right? So since now we know what is the subspace, it means that we can look at a lemma. This lemma says, we have this lemma 2.2.2. We have this lemma that says, the lemma says that a non-empty subset, we know what subset is this, so we're talking about W. non-empty subset W of a vector space V of a vector space V over, should be over a certain field, over a field F, because we're going to need a scalar, right? And we say that this is called, or is a subspace, of V if and only if, meaning we are looking at some biconditional. You say right now, if and only if K V plus, or let me say Ku plus V is an element of W. So this will occur for, let me say, for all U V element of W. If I take U and V vectors from W and I take some scalar K from F, so this will be the case. So for us to prove this, we need to break this into two. We know that biconditionally can be broken into two. It means that I can break this into this case, break this into this case, right? So in the first case, when I break it like this, we're going to have a case where we say that we have the hypothesis. We're going to have the hypothesis, which in this case, our hypothesis will just to be focusing on the case where they say that we have a non-empty subset W of a vector space V over a field F, which is a vector space. So we can say that here on there we can just suppose W is a subspace of V. You see, right? So on the hypothesis, we can just scrap this part to say that W is a subspace of V. And then on the conclusion, it means that this is what we are required to prove. On the conclusion, this is what we will be required to prove, right? On the conclusion, we'll be required to prove that if we take two vectors from W and one scalar from F, then we're going to have this. We're going to have that if I take that scalar multiplied by a vector, I add another vector, I'll find that this is in W, meaning that I'm applying scalar multiplication and vector addition to get this. So I can say we can write this. Let me just write proof. So we start like this. First we focus on that part. So we are saying that first what we're going to do here, right? We're going to suppose that W is a subspace. And we're going to suppose that a non-empty, because already told us that this is a non-empty subset W of a vector space V is a subspace of V. You see that? So this is what I'm supposing. I'm supposing that a non-empty subset W of a vector space V is a subspace of V, right? Or I can even say over some field F. So I say that now I'm going to let, if I take two vectors, if I let U, V be an element of W and let me say a subspace of V over a field F, because I'll need that field, so I also need to suppose it there. And then I'll say K element of F, or you can just copy this whole statement when you're supposing, right? You can just copy this whole statement when you're supposing. You can just copy it. So now I have this, right? I've taken these two vectors. I'm saying that if I take these two vectors, and what's going to happen, this will imply that if I take these two vectors, this will imply that if I take k times u, I'll find that I'll say that this one is found in W. If I take a scalar multiplied by a vector, I'll find that this is in W. And, or let me say, which implies, or not even which implies, let me just say, and if from that same operation I now add another vector, I'm going to find out that this is also in W. If I add two vectors, I find that it's in W. So proving the first part is simple, right? You just have to prove that this is the case. You're just going to prove separately. So now we're going to say that since we have proven this one, we can take the conversely part, right? Now for conversely part, we're going to say this. We're going to suppose now. We're going to suppose. So let's see what is it that we're going to suppose. Let me just use a different color here. We're going to go back to the statement. Obviously, we need to suppose, but we need to know what is it that we're supposing. We're going to suppose now that this is true for all this. You see right now. We're going to suppose that k times a vector plus this vector element of W for all UV element of W and k element of F. So I'm just going to suppose as it is, right? Now I'm supposing that this is true for all this, right? So now the aim is to show that W, a non-empty subset W of a vector space V over a field F is a vector space. So first I need to show that this W is non-empty. I mean, otherwise I need to show that there's a zero vector. When I'm done with that, I need to show that this is a subspace, meaning that I also need to show a vector addition and scalar multiplication. So with this being said, now I'm going to come and say, if this is true, right? If this is true, if we suppose that k multiplied by some vector plus a vector is true, it means that we know that they will exist, or they exist. We know that they exist, or since, let me just say, since k vector plus v is an element of W, we know that they exist. Let me write it in words. We know that they exist. I can choose any vector. They exist a vector V element of W. We know that this one exists, right? And also they will exist U, so you can choose N. It's up to you which one you want to choose. And if they exist V, or I can even choose U, because U usually was the one that came first. I can say they exist U, element of this. And if the vector U exists, it means that also, if I come now and multiply this vector by -1, then add it to itself, you see right now, this would give us, this would be the case plus this. Or in other words, I know that if they exist a vector V, and we know that this is true, it means that it has an inverse. It's possible that it has an inverse, right? Then for this case, we would say that if I take a scalar, just that we won't talk about it being an inverse in this case. We're going to say that if I take a scalar -1, I'm trying to check the negative of a vector space, right? If I take a -1, that is a scalar multiplied by a vector. Then I add by the positive vector, I'm going to get this. And this will give us what? A zero vector. and this is in W because they are both in W. You see, right? Because we know here we have said that this is true. You see, right? If the scalar is -1, why we can even say this, or we can even say that if k is equal to -1, this would be -1 u plus u. You're allowed to add the vector to itself, right? So we can check this. Cu plus u. This would be u plus u, which this would give us a 0 vector, and we know that this would also be in W, and you know that this k is an element of F. We say right. Then now we've shown that W is non-empty, so I can even say hence W is non-empty. Can say hence W is non-empty. So now since I've shown that W is non-empty, let's go back, say that we need to show that W is non-empty, and now we show that W is non-empty over a field F. So we did take some field -1 and show that this is non-empty. And we also took some vector from W. Now we need to show that this is a subspace of V, right? And for us to show that this is a subspace of V, it means that we would need to say that from this case, remember I said that from this case, this one implies that -1 u, which is equal to minus this, is an element of W. Remember, right? This is what we have explained. I think if I check from what I have also from the guide, let me see from the guide, I think they also specified something like that, if I'm not mistaken. I think because I tried to break it down, but then they try to explain it in ways to what they mean. So what they say here, if you can check exactly how I try to summarize it, right? They say that if W is a subspace of V, even though what I did here for you not to summarize things, I just say that you can just suppose that this is true, right? Then you show that if you suppose this, you must show that this is true. So we say that we're going to suppose this, and we say that if these vectors are in that scalar, then we can have this. Obviously, we need to show this first, then we add the vector later. You say that we show this first, then we add the vector, show that that is true. Then we do the conversely part. Doing the conversely, we're going to say that since W is non-empty, there will exist some vector. And we know that from this statement here, we're going to say this. We're not just going to say it's non-empty, we're just going to say that if this is true, meaning that W is non-empty, then we must show that it is non-empty. How do we show that it is non-empty? We showed by this. Then I said hence W is non-empty. You see, then we say that after that, we know that if I had taken K from F and I took a vector from W, we can show that scalar multiplication holds. So we can do that. And this one, we have proven it here, that this is equal to this. And obviously, it has to be in W. You see, right? So we can even come and show by the other vector, say that if this is true, it means that even if I was to take the other vector, it will still be in W. And finally, we can say that if I take these two vectors, I can show that even if now the scalar is not -1, it's +1, I can show that the vector addition does hold. You see, right? So we can go and revisit that. Try it by all means to break it down. So it means that from what we have here, this is true, right? And again, we can say this. We can say that since we have shown, first thing that we showed here is what we showed, that there exists this U since W is not empty, right? Show that there are some elements in W or some vectors in W. It means that it is not empty. And if it is not empty, that given that that vector exists, we can try to choose a scale from f. Then we use that vector to show that if I add it with its own inverse, it means that I can get a zero vector. So now I say that hence W is non-empty, right? Given that it has a zero vector. Now we say that since this is true, we can come and show scalar multiplication. Remember here we're trying to show zero vector. Now we can try and show scalar multiplication. We can say that if I take k element of f and I take u element of w, right, I can imply that if I take that k by this, and we know that there's already some vector in w, this would still give us k this, which is an element of w. We say, right? So in other words, I'm saying that what I'm trying to show you is that if I take two vectors from w and multiply them, then I add by the zero vector, those will still be in w. So this here I would have shown this scalar multiplication, right? So after this, now I can come and show the vector addition. Or even before I say that, we know here that remember this one, I said that reason why in your guide they came here and say in particularly what they say that they chose the other vector to show you that this is equals to minus v, which is in w, which is true, right? Even if you had chosen this vector, it will still be in w. Now it means that now we can show that the vector addition exists. So how do we show that the vector addition exists? It means that I can, if I take two vectors now, I take these two vectors. If I take u and v element of w, right, then I take one, let me say, and one from f, I can show that 1 times u will be equals to u, which is an element of w. So this can give us, if I take 1u plus v, we know that already 1u is equals to u plus v, which this is an element of w. So we have shown this vector addition. If you can check the kind of properties that we applied here, this will apply to the last property number 10, right? We applied last property number 10 here. If you check here, this one is just a vector addition, right? Or I can say if I factor out the 1 here, even this one, it could simply mean that v, if I factor out 1 here, I'll have u plus v. So we've shown some vector addition and distribute the scale. If you check here, let's see what else have we shown. If you check here, we've shown some identity. We've shown some identity here. So we know that if we take this, add the zero vector, we're still going to get that element. And this obviously it's some scalar multiplication. SM1, right? So if we check so far, we've shown 1, 2, 3, 4. And then if we check again, we can say that here we tried to show some inverse, right? We tried to show some inverse, which comes after the identity. And then we've tried to show that, let me see what other thing we've tried to show. We'll see how many properties we try to show. Yeah, I think for now, these are all the properties that we try to show, right? So if you can check, the properties that we try to show are all these. So you can just think of them to how many properties that I need to show that this is like this. So what I used here for me to arrive to the solution, I first used the inverse to show that there's a zero vector. Secondly, I used the identity to show that there's a scalar multiplication. Then thirdly, I used the last property, right, SM10 to show that to show that if there's this one of vector addition, you said that I use this one, and that's why I used them together, right? And another one which is vector addition, it's like a scalar distribution of a vector addition, right? So this is why I use them together. If you can check, you can try to understand what did I apply and so on. So I think based on this proof, you will try to understand it. What can I do? What is it that I need to show? How can I show it? And so on. So it will be simple for you to remember and how to prove. You don't have to prove word by word. You just need to know which points to include.